you want to load all the flip-flops at a time, we require some extra circuit item. So those circuit is nothing but made of gates, combinational circuit. Okay, so that gates will decide how the information can be transferred, right? Now the third point is very important. Just check out. Counters are also special type of resistors, but we have already seen what are counters. Right, we know that counter is nothing but a sequence, especially special sequence it goes on, isn't it? A predetermined sequence of states it goes on. That we have already seen. But now it will be very easy to understand what exactly is a resistor because we have already seen what a counter is, isn't it? Okay. Now, just see. Okay. This is a circuit. Don't look into the text. Only analyze the circuit. In the circuit, what exactly you have? Yes. In the circuit, what you have? You have flip-flops, right? 4 flip-flops, isn't it?
4 flip-flops,
Four,
right?
4 D-type flip-flops. And if you see, is the clock same for every flip-flop?
Yes,
Are
ma'am.
you guys there?
Yes, ma'am.
Yes, ma'am.
Okay. So you have the same clock applied to every flip-flop. Okay. So then it is a synchronous one. We don't know it is a counter or register. We will just find out what is it. Okay. Now what else information you can get from the circuit? Don't check the text. Text is easy. Okay, to understand. First check what the circuit is. Circuit seems to be very familiar. Right. You have some 4 inputs noted as I0, I1, I2, I3, isn't it?
Yes, ma'am.
Okay. So now if I see such type of circuit, first thing what idea I get or anybody will get is it is a sequential circuit. In fact, it is having a common clock pulse. So definitely it should be a synchronous circuit because they are all working on one trigger. That is one common clock pulse, isn't it? And that too it is positive clock pulse. I think so. Right? And afterwards there are 4 inputs, that too it's a D-type flip-flop. So what I can see is at a common clock pulse, 4 inputs enter into the 4 flip-flops and then 4 outputs will be generated, isn't it? Is there anything more there? Or anything more information you are getting from that? Yes.
Then clear, sir.
Yeah. Okay. Clear is an attribute to any flip-flop. Clear means the flip-flop has to be clear. There is no other choice. Every flip-flop is made up with a clear only. Clear is to refresh it, isn't it? So clear is a control input, just like your clock. When you can accept clock is acting as a trigger, clear also is another mandatory one which will clear the flip-flop. It's like flushing out everything, old data. That's all. So in starting of the circuit, we can use clear. Otherwise, if you want to start a new event in the same circuit, we can use the clear, isn't it? Anything else you have seen there? Clear is nothing but your reset thing. Okay. Other than that, what else is there? Anything? Anything else? No, na? Okay. Now, just hold on. This is a D-type flip-flop. What do you expect at the outputs? The same input, right? What is the characteristic of a D flip-flop?
Yes, ma'am.
Yeah, D flip-flop is nothing but a delay flip-flop. It's a simple buffer. Whatever you input, I0, I1, I2, I3, after a delay, A0, A1, A2, A3 is the same, isn't it? Yes or no?
Yes, ma'am.
Okay, so now I can clearly say this 4 connected D flip-flop is acting as a register which stores information I0, I1, I2, I3. Okay, for some time, then gives the same A0, A1, A2, A3. That's all. So isn't it a resistor? Because it's a D type. Nothing else is there. Right? And only thing is to enter the information, we have a clock pulse. Take the output also we can use another timing. Like means we have time sets, isn't it? We have a timing signal and every time after every interval we are No, no. What is the characteristic of a
No.
D flip-flop? It toggles. That means your information will be changed, isn't it? So can I say a D flip-flop is the best suitable for register? Because register doesn't want the information to be varied. It has to take the same information and generate the same information output also, isn't it? Yes or not? Please use analyze. Register means only storage. Don't change the information at all. Don't change the data. Had it been T, the data will be changed. JK, data will be changed. SR also data will be changed. Isn't it? Only best option is D flip-flop. Is that correct? Everybody agree for that?
Yes, ma'am.
Yeah, is that
Yes,
correct
ma'am.
only? Okay, now, so I can say a D flip-flop connected like this, and moreover, wait, hold on. What is this type? Is it a parallel in and parallel out? Can I justify that? Parallel in and parallel out? See, a lot of information we can get from that a particular circuit. Is it a parallel in and parallel out? Hello?
Yes, ma'am.
How do I have to say it's a parallel in and parallel out? Do I have any controls which is parallelly loaded and parallelly coming out? Let's presume. Whoever said yes, I am asking them. Hmm? Yes, is it a parallel in and parallel out? Is it so? Okay, now I will
Yes,
show
ma'am.
another. How, please? Who said yes? I just want to know.
Ayushman.
Okay, so Aishman, isn't it?
Yes, ma'am, because the input for one register is independent of input from other register.
Okay, input of there is no register, ma. There's only flip flop. That flip flop is a
Okay.
4-bit register, you can say, because it is storing 4-bit information. All are connected together. Okay, that's a correction. Then what is that you told? It is what? Come again?
I mean, it is independent of other inputs.
Okay. So every flip flop is receiving its own information, right? Independent. Hold on. That means, do you know at a single stroke it is entering? Are we pretty sure about it? Because it is independent, you are saying it is parallelly loaded, right? But to make it more authenticated, okay, we can say at a single stroke it can be like I can show you a better version than this. This is a raw version of your parallel loaded. Now you can just see this circuit. I'm showing another circuit. Just see this. Just see this circuit. Okay, little complicated. First, analyze that. Analyze this circuit. This one is an authenticated one for a parallel load. Why? Because there is a load control with me, a control signal I have created for myself, so that will ensure that all the information is loaded at a single level. Please try to understand. Is that correct or not? Just check. This is a little complicated one. This is a little complicated, but we have to analyze the circuit, and the resistor is supposed to be parallelly loaded. Okay, how we can ensure? How we can ensure? What happened? Like see, I0, I1, I2, I3 is there. Fine. They are entering into D, but they are not entering directly. They are entering through some gates, and the gates are having a predetermined version. What is that? Clock is untouched. Clock is untouched. Everyone. Now this circuit and the previous circuit, are they both same or they are different? Definitely different. But the work is same. Isn't it? Yes. Everybody are analyzing or just checking the slide? It is a general example. Okay, there is no real analysis there. I mean, no real design there. It's just a circuit I'm showing. Can you analyze the circuit? Is that parallelly loaded? Can you explain the? Understand about the how it works, working style of this particular resistor? See, I can check out. See, there is no difference between this and this. This one and this one. If you want, you can take a screenshot and then check. Is it the same or different? Yes, Aishman?
Different.
Different. How? See, I'll tell you. The
Circuit
previous
is
slide,
different.
yeah, the previous slide, I0, I1, I2, I3. Okay, all are entering into different D flip-flop. Okay, all are, because that all the D flip-flops are there. This is having one block, another block, another block, another block, all D. And these are all synchronized. Same clock. Okay, so that one is anyway common, and afterwards you have information entering into this. Okay, now the new one is also the same, but it is having some control, some superficial or maybe a much authenticated and analyzed version. Did you see that? So here also we have 4, right? But information is not directly entering. Information is entering. First of all, if you check, I0, I1, I2, I3 are not just like that connected. They are connected to AND gate, isn't it? And the other control, this is a 2 input, no? 2 input AND gate. And the other input, what it is doing? See, I0 is connected to an AND gate. This is I0. What is this input? This is what input H1? Just tell me.
Before that, OR gate is
It's coming from? It's coming from what? Hello? It's coming from what? What happened? Am I in the meeting or not? Renmai.
yes, ma'am.
It's coming from what? The second input to the AND gate, which is taking I0. From where it is coming? It is coming from a signal called
From
load,
load.
isn't it? Load. Right? Yes or no? Yes or no?
Yes, ma'am.
Now you tell me, is the load there powerful? It is powerful. Why? Because you just check. Once the load is switched off, it is like very differently given. You have like this. You have level 2. Level 1 is 0. Level 2 is 1. To this particular one, if the load is 0, then what happens? This level is 1 and this level is 0. Right? To this particular one, which level is coming? First level or second level? Check out the circuit. Check the circuit and test. Second level, isn't it?
Okay.
Yes, second level. So that means the load is having a particular authority to control the I0, isn't it?
Yes, ma'am.
Yes. And whereas the other one, yes. And then afterwards, the OR gate is again having a decision factor with a feedback from your previous one. Isn't it? The OR gate. So finally, D is taking an OR version of this and this. So what do you understand from that? Can it be parallelly loaded? You mean to say it is a parallelly loaded? Whereas this one is not parallelly loaded. It is also parallelly loaded. But you don't have any control signal extra. Right? Whereas here you are given a load signal and that load is controlling to keep the previous one or to make a fresh one. Don't you think so? Yes or not? If you want to
Yes,
say
ma'am.
Yes.
yeah, that is what I was telling. See, resistor is a continuous process. Right? Now I am getting back to the old story. Here, I 1000. Okay, I have inputted at 1 clock stroke. Finished. Then what next? You got A0, A1, A2, A3. That's it. Then afterwards, job done. I should have a fresh input ready. Then afterwards, it has to store and it has to give, isn't it? Right? Whereas the new circuit, what I have stored, what I have seen is a feedback process. It is a continuous storage, don't you see? Right? And now you can check the details of it. Just check the details. It is a clock edge type to the C inputs of the registers, like C inputs means clear inputs and all that. Will load 4 control inputs. 4 inputs to be parallel. Okay. For synchronism, it is advisable to control the operation of the D flip-flops. Okay. The 4-bit resistor will load control input. Am I audible now?
Yes, ma'am.
Yes.
There's a recovering also, I don't know what. Okay, fine. So anyway, so register with parallel load, right? This one is also there, parallel you have load, and I have shown you another parallel load, right? Now you tell me, right? Just see, the explanation is provided here. If you want, you can just have a look at it. When the load input is 1, the data in the 4 inputs are transferred, okay, into the register. When the next positive edge of the clock, okay, when the load input is 0, the outputs of the flip-flops are connected to their respective inputs. The feedback connection from the output to the input is necessary because the D flip-flops does not have any change condition, no change condition. Yeah, that's what I was telling you also, right? Now see the difference between this one and this one. Once the data is entered, then job done, finished. Okay, whereas here you have an authentication, like you have a feedback that every clock pulse the same one is getting repeated and restored. That's all. Now I can say this one is parallel loaded, whereas this one parallelly loaded. I'm not saying that it is not parallel loaded, but only once, isn't it? Now I think Ayushman or somebody who has told it is a parallel loaded. Is this information fine? Is this information fine? Hello? You guys can listen?
Yes.
Yes or not?
Yes.
So both the cases I'm talking about the resistors. The second one is, you can say in your language, a hi-fi register. That means information is restored back to back, and it's a continuous process. And this is a one-time process. Okay, now another level I'm telling you. If I want to transfer all this information, for example, I'm just saying, okay, I'm going to next level of changing. I have one resistor, right? Resistor A. I'm now not talking anything extra. There are some flip-flops in that. Okay, I have a 4-bit register. I'm writing here 4-bit. That means it has some 4-bit information. I have a register named B. It is also 4-bit. This is empty. This is filled with 4 bits. I want to transfer all this content into this content. Please try to understand. I am showing in blocks. Are you there? Yeah. Okay. So from register A to register B, I had to transfer information. It has 4 bits, some values. And this is empty, this is filled. How I can transfer? There are many ways. You can tell your inputs. See, I have to transfer 4 bits. So I have option all the 4 bits at a time I can transfer. Otherwise, I can transfer one after another. So when I transfer one after another means the first register will be getting emptied, the second register will be getting filled, isn't it? Yes or no?
Yes, ma'am.
So 2 options. First option is collect all the 4 bits and then dump it there. Another one is bit by bit, one after another, I will transfer into this till this one is filled and this one is emptied. There's a third beautiful option where it will be transferred and restored also. That means I can transfer bit by bit. At the same time, the same bit will be restored. So what is that? Even if I transfer here, it will not get empty. It will retain its information. At the same time, information will be transferred. Don't you think this is a beautiful concept? That means we have a backup and we can have a transfer. This type of things. Understood this one? We have a backup as well as we have a transfer. This type of information is called a shift register operation. My job is to shift only. Shift from one content from one register to other register. But at the same time, I am using a smart analysis here. I am retaining the information as well as transferring the information. What? It is for a backup, isn't it? Why you guys are recording? For your backup, isn't it? Yes or not?
Yes, ma'am.
Right. Now hold on. Can I have all the information at a stretch dump into that? Now okay, that is a pretty big task. So because I have to collect all the information, then at a time it has to load. It is really tough. Shift registers will go bit by bit only. That is definitely. Now tell me, let us consider each bit requires 1 clock pulse to transfer. That means each clock pulse is dedicated for one transfer. So now 4 bits have to be transferred. So how many clock pulses I will waste? 4 clock pulses, no? So entire information to be transferred into this, I require 4 clock pulses, isn't it?
Yes, ma'am.
Each one stroke, one bit came here. Another stroke, another bit. Third stroke, another bit. Fourth pulse, another bit. So all the things are transferred at the same time within the same clock pulse. It has been retained also. Right. So this type of operation is called just serially input and serially output. This is also possible. Yes? Yes or no? Can you identify here? Serial input is coming as well as serial output is also going. This type of transfer is possible with a shift registers. Isn't it? Are you guys understanding or not?
Yes,
Are
ma'am.
you guys listening? Yeah. Right. So now we can just check out the simple information. A shift register is nothing but it's a register capability to shift the information, right, in both directions. Right. Hold on. Here one more point I have to cover. If I want to transfer from this to this, I am doing here. Okay. Now, can I say this is one-sided operation? This is what? This is my left side. So this is shift left. Can I say this is shift left? Right? Hold on. From register B to register A. This is having information, 4-bit information. It is transferred as well as it is restored. Can I do this? Shift left. Is it correct? Is this correct or the previous one is correct? This is correct?
This one.
Right. So that means from register A to B I can transfer or register B to A also I can transfer in a smart way. I will retain the information and I will do that. Okay. Now if at all, simple example, I will take each time I can transfer one, like this is one clock pulse, this is another clock pulse, this is another one, this is another one. Each clock pulse will take 1 bit to transfer. Right. So, in fact, I am using 4 bits to transfer. I am using 4 clock pulses. If I have 6 bits, and by the way, I didn't give you the timing of this. Right. All are equal time. Let us consider all are 1 nanoseconds or 2 nanoseconds. We can maintain that. Okay. So, 6 bits, if I want to transfer, how many clock pulses I require? How many clock pulses I require? 6 clock pulses. Isn't it? So, this particular option which can shift right and shift left, these are the specific registers. Okay, now check, coming back to the shift register operation, just check out here. Simplest possibility. Now I'm just showing you this. Just check out this. I have a group of flip-flops connected like this. Can I say this is a shift register? I mean, shift register we cannot say. Serial in, serial out, 4-bit flip-flops. Isn't it? 4-bit together. They are stored. Only D flip-flops I have used. Just check out. Can I say it is a shifting operation is going on? 4-bit shift register also I can say this word. Isn't it? Can I say that? Can I say or not? Are you guys there? Mohit? Amrit? Just checking out whether you guys are listening or not.
Yes, sir.
So can I say this is a shift register? In fact, more than shift register, just check out whether it's a serial in and serial out coming out. Because intermediate I am not counting. Just see. D. 4 D's are there. I am not connecting at the in between. Say it's like this. I have D, I have another one, I have another one, I have another one. I am only connecting like this. And finally, I am collecting here. I am connecting like this and collecting at the output. Only one time I am collecting. I am not collecting intermediate. Right. So I will load a serial in, right? A bit called 1. Consider. And these are all synchronous. Right. Now tell me, after how many clock pulses I will collect that particular 1 here at this point? Yes. 4. And moreover, what is this called? Which side it is shifting?
Right.
Right, it is shifting right for you. Okay, I'm also facing you the board like this, and it is shifting right. So this one particular one, what is at the input side, will go to the next one. So this is flip-flop 1, flip-flop 2 will receive in the second pulse, flip-flop 3 will receive in the third pulse, flip-flop 4 will receive in the fourth pulse, and at the fifth pulse or the fourth pulse itself, we don't know what is the sequence is, we will collect the output. Isn't it? Yes or not? Right. So I can say it is a shift register operation, shift flip-flop operation. We can say that. Now, just check out this. Right. Now, serial in and serial out is there, right? Now, can I say the word called serial transfer? Just see this. This is what I was trying to tell. Shift register A, shift register B. Okay, I will serial input as well as I will serial output. At the same time, I will take the shift register B also and then collect it. Input it as well as collect it. My final destinations are 2. One is in the register A, serial output, and serial output at the register B. But if you see, serial output at the register A is again fed back. Isn't it? Yes or not?
Yes, ma'am.
Yeah, this is what I was
Yes,
trying
ma'am.
to explain. Yeah, this is called a serial transfer from one side to another side. I can just give you a small example also. Right, now just see, check on this. These are the clock pulses. Right, now shift control operation and clock. Can you just see here, serial transfer from register A to register B. Can it happen in this? The timing diagrams. Can you identify what does that means? Clock pulse is a continuous one, right? Now afterwards, see, this particular signal is there. Okay, for this clock, shift control, and then this one, the timing diagram. Just check out this. There are two clock, two words. Just see, CLK is different and clock is different now. CLK is a big CLK. If you want, you can take a screenshot. The CLK is different and the clock is different. CLK is a combination of these two, then only CLK will be generated, isn't it? Have you checked
Yes,
it?
ma'am.
Yeah, CLK is different from clock. Please try to identify it. Now you identify it. Yes. CLK is the combination of these two. So when the combination will come, when the shift control will identify, then only it will start, isn't it? Just see, clock is the combination of these two. You do the end operation here. So totally here, after every pulse, it will get shift control and clock together. At this till this level, it is 0. At this level, it is high. So it will take different timings for each one to transfer, isn't it? Okay.
Yes,
Now, yeah. Now I'll just give you this one. Now just see this particular one. Examples. Just an example. A timing pulse is there. Initial value some 1011 is there. Shift register B is having 0101. It's just an example. Right. After time 1, after time 2, after time 3, after time 4, what is happening pertaining to that diagram? See. Here, what exactly is given? We have a resistor A. We have a resistor B. We have both controls going here, right? And then afterwards you have a serial shift back also. This is CLOCK and this is shift control, something. And here they use the word called CLK. Just for nomenclature, nothing to worry much. So initially, there is some information here, there is some information here. So that initial one is already there. What is that? 1011. And that particular one is having 0010. Okay. Now, after T1. T1 means what? The pulses what I have shown. Timing diagram. What is happening? There is a change. Can you identify what is the change? According to this, this particular one has to come back. Yes, that means it has to shift. So this will shift here. This will go here. Right? This will go here. Isn't it? Is that correct?
Yes, ma'am. Yes, ma'am.
Easy. So that means what is happening? This is coming here. This is coming here. I can show like this. And this is coming back. That's why I'm showing after T1. Yes. Right? At the same time, this is entering this also. This is entering this side. So what happened? It took this place. This will go here. This will go here. This will go here. This will be kicked out. Is that correct?
Yes, ma'am. Yes, ma'am.
So that is what happens. Clear? Right. So here this will be easy for you. Now, next. After T2, I am not using any timings here. I am using the words T1, T2 so that you can understand this is the next one. Value of that I am not giving. Afterwards in the problems we can do. At T2, what will happen now? At T2, now reference is this now. For this is the situation, status of this, isn't it? Now what is happening? At T2, don't check there. Don't check, see the slide. Just check on the board. You can see board also, no? Parallel. Yes? This will be here. This will be here. This will be here. And this one will be coming here. Is this the condition? No?
Yes, ma'am. Yes, ma'am.
This 0 will be here. This 1 will come here. This 0 will be here. This 0 will be coming here. And this 1 will be kicked out. Is that the condition same? See, I may be wrong. You can tell me. It's not matching there. T1 is fine. T2 is not matching.
No, ma'am.
Mine is correct.
Ma'am, 1100.
Why 1100 is coming? That is what I was wondering why.
Because it is series input, right?
Series input. So
In T1, N is like 1. So 1 will be inputted to register B.
yeah. T2. So this one will go to the input already done. So at this level, what will be here? Which one will go? This will come here as well as this will go to this. No? Yes or no? See, this arrow is wrong.
From the previous one, it should have
Yes,
been.
yes. This arrow
This
should
one
be.
will be.
This should be the correct one, isn't it?
Yes, ma'am.
This arrow. That time why you are listening then? No, nobody said it. Okay. Clearly, I gave you the answer. Here I was telling in the reverse manner. Then also nobody pointed out. What happened again?
Ma'am, disconnected in the middle, I guess.
Middle. Again disconnected or any dramas are going on?
No, ma'am.
Huh?
No, ma'am, the video got stuck.
Video got stuck.
Yeah, I don't know what is happening. Na? Seriously. Now, T3 is fine. That time T3 explanation was there. Is that okay?
Yes, ma'am.
Okay. Now T4. After T4, one question. Can you tell me what is the content in register A and register B at T6? T4 is done. T4 you can do that. See, again this is 1, 0, 1, 1. Out. Right? That is fine. Right? T4 is done. Go to T5, go to T6. Now tell me the T6 values.
1110.
I don't know. You have to get it correct.
1110.
Ma'am, same as T2.
Same as T2. So that means it's very clear that after every clock pulses or every timing, we get check out, right? I mean, there will be a repetition also. Saving repetitions are there. So now this is a cool transfer, right? Serial transfer from one register to another register. So today what I was telling is registers are very clear to store the information. We can have a smart loading of that, okay, and retain the information, and we can have a transfer of the information serially, right? Hold on, can I do it parallelly? It is a serial transfer. Can I do parallelly? Just think. Parallel transfer from register A to register B. How it is possible? I need some extra things, isn't it? Don't I require some extra circuit? Yes.
Load.
Pardon? What do you require? Somebody is answering? Abhijit? Hiranmai?
Hello,
Yeah.
hello, ma'am.
Yes, ma'am. Can
In
I
parallel,
have yeah, parallel, please.
load. I think load should be there.
So we have to have some extra circuits, isn't it? Parallel loading, parallel transferring. It is possible, but we require some extra connections. Don't you think so? Extra circuit we require. Connections, isn't it? So that it will parallelly transfer every information, right? So nowadays you guys are transferring. Now, for example, I'm telling your language. You are using a pen drive, isn't it? Now tell me how the pen drive is getting loaded, the data from the computer to the pen drive. You have any idea? How it is getting stored? What happened? All are silent. Arey, this is your generation work. You guys don't use pen drives?
Yes, ma'am, we use.
No.
You use, then how? How it is getting stored? No idea, no clue, isn't it? Huh? Okay, now it is done parallelly or it is done serially? No idea. Okay.
Serial.
Serially, that means parallel options are not there, but parallel seems to be faster. Don't you think so? Anyway, doesn't matter. Now just check out. Check out if you have any information you can tell. In parallel mode, information is available from all the bits and can be transferred simultaneously. Okay, in serial mode. Parallel mode is also there, serial mode is also there. But you guys are stuck to only serial mode. How it is possible? Only serial it is done? It might be having a parallel transfer also. We don't know. Isn't it?
Ma'am, in its name, USB, it's serially, so.
Done serially. Okay. Right. Parallel is also possible, but it is done only in the register level in your processor, not for the USB. Inside the processor, inside the compilations and all, that time parallel transfers is possible because that level circuit is there inside your CPU, but not for this USB thing. Okay, so fine, good option. Now, just the thing. Check out this circuit. Okay, this circuit is doing some nonsense. Just an example. Right, there is a shift resistor called A and there is a shift resistor called B. Both of them are supporting a full add. Can I say this particular circuit is doing a serial addition option? This is one of the thing. I think who is that? I think Sankalp is there, or who has told me to check out on this? Like somebody has told to discuss this one. I'm not remembering his name. Is that Sankalp? Starts with yes only. Last time I gave you this problem, right? So now check. Last time I had given you only the full adder and the D circuit. I don't have these additions. Okay. Anyway, now tell me what is the analysis of this particular circuit? What exactly is doing? FA stands for full adder. Actually, the circuit is half cut, right? Isn't it? The feedback is cut. Hello? You guys are there?
Yes, ma'am. There.
Yes, ma'am.
Yes. Is the circuit half complete? Just a second. Let me find out what is the truth. I copied it. What is it? I think this Windows is getting shared. I am not sharing this. Okay. Now just check the serial addition how it is going on. By shifting the sum into A, while the bits A are shifted out, it is possible to use the resistor for storing both the argument and the sum bits carry this one. Now see here, you might be wondering that when you are doing addition, okay, let us consider we have x, y, z. X plus, right. So full adder can do this, right? But intermediate additions also I wanted to store. Can I use resistor there? Hello?
Yes.
That is what I was trying to tell here. Shift resistors or the registers can be used in this one. There's a missing there. There's a missing circuit. Did you see here there's something missing? This S and C, sum and carry, is connected to something else. I will show you that. This cropped out. Can you pull up that? Where the S and C, sum and carry, is getting connected to the D flip flop. Yes. Okay. I'm just showing the explanation. Just see this. The carry out of the full adder transferred to the D flip flop. The output of the D flip flop is then used as a carry input to the next pair of significant bits. So now you can understand what is the connection is. Isn't it? Yes or no?
Yes, ma'am. C will be connected to D.
Yeah, that's right. See, in the cropping it went down. But who is connected to C? I mean D?
C.
Sum is, no. Sum is connected to D, no? The carry out of the full adder is transferred to D, and the output of the D flip flop is then used to carry. Oh, okay. The sum is connected and the carry is connected. Okay, got it. So x plus y plus c. Okay, there are two x and y are coming from register A and B, right? And the third bit is appended. Okay, it's transferred, isn't it? Yes or not? X and Y is from resistor A and resistor B, and the Z is coming from D. Is that correct? Z is coming from whom? Please check out.
D.
Yeah, that is coming from the D. So is that identified like what I should say? Parallel, full adder. Remember that binary parallel adder? Can I take that as a binary parallel adder? You guys have forgot the combinational circuits? A1, A2, A3, A4. Okay. B1, B2, B3, B4. Right? Let us consider A's are supplied from resistor A, B's are supplied from resistor B. In the combinational circuit also, this circuit I have shown. This is full adder, this is full adder, this is full adder, this is full adder. Okay? We have a carry input. This is a fresh input. Right? Now, this one has to go and serve as another input. This plus this will go for sum and carry, isn't it? Did we get this or not? This is carry out. So it is coming, this is sum 2 or sum 1 we will say, sum 2. This is carry this one. You remembered or not?
Yes, ma'am.
Yeah, this is carry 2. So this 2 and then we will get carry 3. This is sum 3. This is serving as an input here. Is that purpose solved there? These are all coming from resistor A and resistor B, and these are doing the full adder work. And who is taking care of this carry propagation? Flip-flop D, no?
D. D.
That's all. So that time it was a what? Halfway through, half cooked. Now you can understand from where these are input, from how this is carry forwarded, and how the clock is controlling the full concept. So this is just a full example of a binary parallel adder exactly worked out with the resistors and clock pulse. So we cannot say a combinational circuit is different from sequential. Sequential operations are performed and combinational is a part of that. That time binary parallel adder was something different. And now you see, this is the actual binary parallel adder with timing, everything, isn't it? Is this explanation, serial addition, you see how the serial addition explanation is given? The output of the D flip-flop is then used to the carry input. Wordings might be different. Okay, but who is solving what purpose is clearly mentioned, isn't it? This is how the sequential additions are going on. Right? Now, just a second. Is this the table? We can get that. Serial adder. X and Y are inputs from the registers. Right? Q is coming out from the D flip-flop. And then sum and carry. See, this J and Q is there. No, this one not required. Just tell here. Serial till S sum. Oh. Did I use JK flip-flop? No, no. J and Q, J and K is there. This you forget. So only this one you can check. We can take two inputs from two registers. Sum them up, that also we can take it, output we can take it. Then afterwards the carry in, we can take it from the register, from the flip-flop output as a third input to this one, previous one what I have shown. This is just an example, this one you can omit. Okay, this one you can avoid, this one you can take. Is this one clear? A clear understanding is given on this full adder with the D flip-flop? Yes or not? Hello?
Yes, ma'am.
Yes.
Clear? Okay, so this is what registers are all about. Right? Now, you have a next class, right? Okay. You have class? 4:15 class?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, tomorrow we can meet. Yeah. So we'll get into the next class, no problem. You can read a bit of registers. Thank you.